Hello everyone, it's a pleasure to be here today. My name is Vsevolod Peysakhovich, and I'm excited to present our research with Mathurin Franck, Maëlis Lefebvre, and Raphaëlle from ISAE-SUPAERO, Toulouse, France, on virtual teleoperation performance under load factor in real flight. Thank you for taking the time to join the session, and let's get started. As unmanned aerial vehicle or UAV operations continue to advance, airborne control is becoming increasingly critical, particularly in military and high-stakes missions such as future combat air systems. However, real flight conditions, especially exposure to high G-forces, could affect an operator's ability to control UAVs effectively. This study examines the impact of load factors on virtual teleoperation performance, addressing a key gap in current research. By understanding these effects, we aim to enhance operational reliability and optimize human-machine interaction in dynamic flight environments. Operating a UAV from a flying platform exposes the operator to varying load factors due to the aircraft maneuvers. Even at moderate G-forces, research shows significant impacts on sensory motor performance. Increased load factors can lead to greater manual control errors, altered force application at movement initiation, and disruption in neuromuscular control and body orientation perception. Additionally, the Coriolis effect, in turn, can cause disorientation, reducing situational awareness. Beyond the effects of G-forces, UAV teleoperation from a moving aircraft introduces challenges related to motion sickness and cyber sickness. Coordinated turns create vestibular visual conflicts, where the body perceives itself as upright, while the external world appears tilted. Head movements can intensify disorientation due to the Coriolis effect, while turbulence adds further discomfort through low-frequency oscillations. In teleoperation, a triple visual vestibular discordance occurs. The body feels upright, the outside world is tilted, and the UAV's orientation differs from both. Unlike pilots, UAV operators do not control their own movement, increasing the risk of disorientation. Understanding and mitigating these effects is essential for maintaining operational performance. In this work, we also examine how aircraft movement influences UAV teleoperation performance through spatial compatibility. According to the Simon effect, reaction times slow down when a stimulus is spatially misaligned with the required response. In flight, an aircraft's turn direction may act as a spatial distractor, making UAV control more challenging, especially if the UAV must roll opposite to the aircraft movement. We hypothesize that such spatially incompatible turns will degrade performance due to cognitive interference. While previous studies have explored this in control settings, no real flight research has addressed this interaction, making our study a critical step in understanding operational impacts. Selecting the right perspective for UAV control is crucial. The first-person perspective, or 1PP, commonly used for piloting, provides a realistic onboard view, but may limit situational awareness. In contrast, the third-person perspective, or 3PP, offers an external view, enhancing spatial awareness and improving performance in dynamic environments. Research from video games and VR suggests that 1PP is better for precise control, while 3PP adds navigation and movement-based tasks. Given that load factors and motion can alter an operator's perception, our study investigates whether a 3PP interface could enhance teleoperation performance under real flight conditions. To investigate UAV teleoperation under load factor, we conducted an experiment with 14 participants from French Aerospace Engineering School ISAE-SUPAERO. Using a Robin DR400 aircraft, we induced load factors while participants controlled a UAV via gamepad and tablet interface. The study compared two visual perspectives, 1PP on the left and 3PP on the right, to determine which provided better control. Participants piloted the UAV through obstacles while performance, workload, and motion sickness symptoms were recorded. To examine the effects of gravitational forces on UAV teleoperation, we tested three load factor conditions by varying the aircraft bank angles. The actual forces were measured using the eye-level system, confirming values close to targets. Additionally, we tested spatial compatibility, comparing scenarios where the aircraft turn matched or opposed the UAV's required movement. This allowed us to analyze how spatial congruence impacts teleoperation performance. In this study, participants first underwent ground and in-flight training to familiarize themselves with the task and flight conditions. The experiment required them to control a UAV roll during turns with varying load factors and visual perspectives. Trials were conducted in both first-person and third-person views under different bank angles, 30 degrees, 45 degrees, and 60 degrees, resulting in load factors of 1.1 G, 1.3 G, and 1.9 G. Between trials, participants performed a monitoring task to maintain situational awareness. Performance was assessed through accuracy metrics such as absolute and silent error when aligning the UAV with obstacles, response time, time taken to reach 10% or 50% of the required tilt, cognitive and physical demands through self-reported motion sickness, mental workload, and physical strain measures. And we performed a repeated measure ANOVA, analysis of variance, to analyze the effects of three key factors: load factor, spatial compatibility factor, compatible, incompatible, and neutral conditions, and visual perspective, first-person versus third-person conditions. Our findings reveal that teleoperation performance remained stable across different conditions. Specifically, we found no significant impact of load factor, spatial compatibility, or visual perspective on task performance. Likewise, neither spatial compatibility nor visual perspective influenced participants' subjective experience, including mental workload and motion sickness. However, load factor had a significant effect on subjective experience. As G forces increased, participants reported higher physical and mental demands, as well as increased motion sickness. These results highlight the importance of considering operator comfort and endurance in high-load environments, even when objective performance remains unaffected. Our results suggest that visual perspective had no significant effect on performance, possibly because peripheral visual cues helped mitigate the adversary effects of intersensory conflict. However, spatial compatibility also showed no significant impact. The focus on the tablet may have reduced the effects of peripheral visual conflict, but this could have conflicted with the advantages of peripheral awareness. Regarding load factor, participants were able to adapt their performance despite increased G-forces, but their subjective experience was clearly affected, with higher mental and physical demands as well as increased motion sickness. Looking forward, future work should focus on expanding this sample size and increasing task difficulty to better understand the relationship between load factor, spatial compatibility, and teleoperation performance. Thank you for your attention. If you have any questions, feel free to reach out.